hard to
Visually, let's look at a graph.
So when you're in the car, you think about it when you're driving the car.
Like the only thing about tonight is, I might work on this night, so we're going to work tomorrow morning.
Back when I was a young lad, people, not that anybody's doing this, but we used to all drag race Friday night. We'd go out drag race. If you've ever raced in a car very much, or just put the foot on the floor, you initially accelerate real fast. The acceleration starts decreasing pretty quickly. Part of that is because you got increased friction. The faster you go, the more drag you have. Part of it's due to that. But most of it is due to this equation. The faster you go, the more energy you have to put in to go that next leap up. You have to put more and more and more energy. When you think about something like the space shuttle that's going around the Earth, or used to, I guess. I don't know if it's still, they're still running those things. It's going so fast. It's got the velocity turn. It's just enormous. It's a pretty good sized mass. It's a ton of energy when it's coming into the atmosphere. All that has to be burned off. It all burns off in heat. It's amazing to me that thing comes down in one piece. I mean, you can guess the mass, you can guess the velocity, you can calculate the energy. It's just absolutely enormous. Which is why they have these huge big rockets to get it up there in the first place. I mean, just an enormous amount of energy. So let's work this one. You just got a couple of minutes there. Oh, what was the answer to that? 800. Okay. So the previous one. $800 joules. So this is just like the spring. You can't just say, well, we're going to go from 2 to 4, so it's an increase of 2 meters per second. Doesn't work. It takes one energy to go from 0 to 2. It takes more energy to go from 2 to 4. It takes more energy to go to 4 to 6. More from 6 to 8. And this is really why your acceleration decreases, like in a vehicle. You've got a 200 horsepower engine, up to 30 miles per hour. You don't have a whole lot of wind resistance compared to everything else. But you're already really slowing down. Your acceleration is slowing down. So let's work this. Kinetic energy is 1/2 mv squared. So it's 1/2 times 100 kilograms times 4 meters per second. So 1600 divided by 800. Oh, that was the answer to this one. Somebody told me it's 800. What was the previous answer?
Oh, I thought you were talking about this.
Yeah. It was 200. Okay. So what's the difference between the two? Once you get to 4 meters per second, you've got 800 joules of energy, of kinetic energy. So the difference, the delta kinetic energy, is 800 minus 200 joules. So it's 600 joules. So the first 2 meters per second costs you 200. The next 2 meters per second costs you 600. See how expensive going increasingly faster costs. It takes a lot more energy the faster you go.
Isn't it exponential growth?
Yes, it is.
So now the linear is just...
There's nothing, it's m times v squared. Nothing's real linear on here.
I guess I was
Okay. The spring, the force on, I think you're talking about linear, that was the force on the spring. The force is linear, but the energy and movement increasingly is not. There's supposed to be a S there. And it's work. $2.14. Let's just stop here.
How does that happen?
These classes go fast.